Hi, APC Chemistry. Today is a day where we're going to talk about taking a whole bunch of information and putting it together. So, we're going to look at some acid in water reactions, base in water reactions, and then we're going to look at acids and bases together as a reaction. So, we're going to kind of build as we go. Now, these calculations are very similar to the equilibrium calculations that we have been dealing with. They can be complicated. It can be complicated to figure out where to start and where to go, because what you're doing is you're synthesizing so much information and putting it together. So as we go through these problems, you really need to think about what parts of the problem are going to come together. So remember, there's really three main things that you're going to need in every one of these problems. You're going to need a balanced reaction. You're going to need a K equation for that balanced reaction. You're going to need an ice chart, right? Now, beyond these things, you might incorporate some other pieces of information. You're going to have to evaluate, am I dealing with a strong or weak substance? Am I dealing with an acid or a base? Or maybe both? Do they give you information about pH? Well, then the pH equation may help you. Are they asking you about a hydrogen concentration? Well, then you may want to use your KW equation. Or maybe it'd be more convenient to use the pKw equation. So, I mean, just off the top of my head, I can already list a bunch of things that might play in. We might utilize these things to get a piece of information that we want to get. We might utilize these things to mobilize us to a piece of information that we want. We might have to kind of trade out pieces of information through some of these relationships. So there's a lot of pieces that are coming back together. This is a really good example of skills in your life where you're going to have to try and get stuck and ask a question, and then get yourself to the end. Try, get stuck, ask a question, get yourself to the end. And the more of these you look at from all the different angles, all the different explanations from me, from your book, from your classmates, from explanations online, the stronger you're going to be at these. This is a skill. It's going to take some practice. This kind of launches us into the next three chapters. Then chapter 14, 15, and 16 really are just looking at the same problem from a million different angles. So we'll start with some easy ones that just use a couple pieces of information, but keep all of this in mind as we're approaching these calculations. It's kind of a logic puzzle. It's kind of a Sudoku puzzle. So just keep trying these angles and ask your questions. Okay, so in this example, they're going to ask you to calculate the pH of strong acid solutions. Now, this is a really important thing to distinguish in your mind. How does a strong acid versus a weak acid act? Now, we already know that a strong acid is going to have a very large K, but you need to fit the concept to that. Why does it have a huge K? Because ultimately the entire acid dissociates. The entire acid reacts with water to form products. So you may start with an amount of your acid, I don't know, like 15 moles or something like that. In a strong acid solution, you're all 15 of your initial quantity, your entire initial quantity is going to react and form products, and you're going to have virtually none left. That's how we're going to treat a strong acid solution. Now, that's going to be different than a weak acid solution. The very definition of what a weak acid is means that some of it dissociates, but not all of it. And it's going to hit an equilibrium. So how would a strong acid versus a weak acid change? Okay, well, the initial might be the same, but your change is going to be different. With a weak acid, not all of it will dissociate, right? Only part of it will. So you either have to know what that change is, or you're going to have to use an X. And then your equilibrium position will be whatever your initial one is minus your change. So that's the first thing that you really have to divide in your mind in order to correctly deal with these solutions. Now, we have been talking about this for a really long time. Think way back to the beginning of the year when we talked about electrolytes. We talked about what a strong electrolyte is, that turned on the light completely, right? We talked about a weak electrolyte that turned on the light partially, and we talked about a non-electrolyte that wouldn't turn the light on at all. Remember, we were talking about when a light bulb is attached to some power source, and then its electrodes went into a solution. Well, if that solution contained ions, then the ions would help the electrons jump and complete the circuit. If the solution did not contain ions, though, then the electrons could not jump from one wire to the next, and it would not complete the circuit, and the light would not turn on. That would be a non-electrolyte, like sugar was a good example of a non-electrolyte. The strong electrolytes would provide lots of ions, turn on the light bulb completely. The weak electrolytes would provide just a couple ions, and so the light would be really dim, right? And so we talked about what kind of things are strong electrolytes, what kind of things are weak electrolytes, what kind of things are non-electrolytes, and this is exactly what we were talking about. Strong electrolytes are going to be strong acids because they dissociate completely, or they react completely and produce all ions, right? Same thing with strong bases. And then same thing with very soluble salts. All of those are going to, whatever you have initially, all of your reactants are going to react or dissociate completely and into ions. All of your initial amount is going to completely form ions. You're going to have lots of ions floating around, lots of things for those electrons to bounce off of. Your light bulb's going to be very bright. Weak electrolytes would be weak acids, weak bases, and slightly soluble salts. Because these things only dissociate or react partially. So they're just going to form a couple ions. The light bulb is going to be very dim. Non-electrolytes would be insoluble salts, soluble salts, and molecules, right? Molecular things that don't break apart into ions, like a molecular solid like sugar, where every point in the lattice is a molecule. When the intermolecular forces between all the sugar molecules dissolve and break apart, you're left with sugar molecules, right, that are no longer attached to each other. But those sugar molecules aren't charged. They can't carry electrons. Your light bulb's not going to turn on at all. So we've been talking about this idea that strong acids dissociate or react completely, weak acids dissociate or react partially. Since the beginning of the year, we now need to take this information and apply it in these problems. All right, so if we have a strong acid, we know it's going to go to completion. And so what we need, our next step in the problem is to think about what's really there. What could be contributing to the hydrogen concentration? Remember, if we're trying to deal with pH, we really need to determine what the hydrogen concentration is. So one of our first steps is to pause and consider what's there that's going to contribute to the hydrogen concentration. Step 2, we're going to, once we kind of tally up what's there, then we need to think about what kind of things are major players. What will contribute to the hydrogen concentration, what will not contribute to the hydrogen concentration, and then we can calculate our pH. So this little calculation of calculating pH becomes kind of complicated because you have to take all of these considerations and concepts into play before you can just plug in an answer and chug out an answer. Plug in H plus concentration and chug out an answer. Okay, so let's look at an example here. We have a 0.1 molar HNO3 solution, and we want to calculate the pH of that. So we're going to start by thinking, okay, HNO3 solution, what's present? Okay, HNO3 is present, but I know that it's a strong acid, right? And so a strong acid is going to dissociate completely, and I'm going to get H plus ions and NO3 ions, and my HNO3 is not going to be there in the end. I also have water that's present. We know that HNO3 is going to dissociate completely. We know that water self-ionizes, and so our H plus concentration from water is going to be about 1 times 10 to the negative 7th molar, right? So now that I know what's present, I can set up my 3 crucial things that I set up always: a reaction, a K equation, and ice chart, right? So once you know what's present, you can set up any reaction that's convenient. So for this one, it's really straightforward. Our reaction is just going to be HNO3 goes to H. Well, actually, let's do HNO3 reacts with water to form H3O plus NO3 minus. Now I started to write HNO3 goes to H plus NO3 minus. Remember, we basically treat H3O plus and H plus as synonyms. They're pretty much interchangeable, right? So, and remember, water is a liquid. And so in my K equation, you're going to have H3O plus or H plus. You're going to have NO3 minus, and then you're going to have HNO3. So in both cases, your K equation is going to look the same. You really can set it up either way. Okay, now I'm also going to set up my ice chart. Okay, so I have 0.1 molar HNO3. When they give you an initial concentration, you're assuming that that's what the concentration is before the reaction starts. So before we mix things, when we have all our separate solutions, how much of each thing do you have present? Well, I know I have 0.1 molar HNO3. I kind of get to ignore water because it's a liquid and it doesn't affect my K equation. And then I'm not going to have any H plus or NO3 minus, because remember, this is the amount before the reaction happens. Now, what is my change? Well, that depends. Do I have a strong acid or do I have a weak acid? So HNO3 is a strong acid, which means by definition, it's going to dissociate completely. So my change will be all of it. If I lose 0.1 of HNO3, because it's a 1 to 1 to 1 ratio, I'm also going to gain 0.1 of my hydronium, and then I'm going to gain 0.1 of my nitrate. So in the end, I will have no HNO3. I will have 0.1 of my H3O plus, and I will have 0.1 of my NO3 minus. Okay, now, does this add a significant amount of H plus? Well, let's see. Let's say that the water also dissociates all by itself. It self-ionizes, and it adds 1 times 10 to the negative 7th molar. If we add these two things together and then we round off to 2 significant figures, what do I get? I get 0.10. So does the self-ionization of water contribute significant H plus? Not in this example, it doesn't. It's not even close, right? You get 0.10000001, and we're going to round that off to 0.10. So no, the water is not adding a significant amount of H plus, so I can just ignore it and just use the H plus that is produced by HNO3. So now I plug in, so pH equals negative log of 0.1, and my pH is going to be 1. Ta-da! We did it. That's how we do this specific equation. So the math is pretty simple. We wrote an equation, we wrote a K equation, we wrote an ice chart. Now in this case, did we need the K equation? Not necessarily. We didn't need the K equation. So as you get better at these, you may choose to not write out certain pieces of this that you don't need. But in the beginning, it is helpful to write out a balanced equation, an ice chart, and a K equation, just so you have all the pieces there as you're moving forward. Like I said, as you get better at these equations, you might realize that you're not using pieces, and you can just kind of leave them off as you consider them and then realize you don't need them. Okay, let's do it again with B. This would be a good time to pause the video and try B on your own with all of these different considerations that we've made. All right, so I have HCl. It's a strong acid. I know it's going to form H plus and Cl minus, and I'm not going to have much HCl in the end, right? I'm also going to have water that may or may not contribute a significant amount of H plus. So I'm going to write my equation, HCl. Let's include water. You can tell that when I do these on my own, I don't normally include water, but I'll write it out for your sake so we actually get the real concepts the first time around. Okay, I know I have 1 times 10 to the negative 10th molar HCl. I can ignore my liquid. It's a strong acid. It's going to dissociate completely. I'm going to have none of this left over. Okay, so from HCl, this is what I would end up with. I will end up with 1 times 10 to the negative 10th molar H3O plus concentration. Now, again, we got to consider that's just from H plus. Do I have any other significant sources of hydrogen? So remember, water self-ionizes into hydrogen and hydroxide. So, and when it does this by itself, it's going to produce 1 times 10 to the negative 7th. So is that a significant source? If I add the amount I get from hydrochloric acid plus 1 times 10 to the negative 7th plus the amount that I get from water, I'm going to get 1 time, I will get 1.001 times 10 to the negative 10, good heavens, 7th molar H3O plus. So in this case, yes, water adds a significant amount of hydronium ions. We have to take that into account. If we don't, our pH is going to look very different. And my pH is going to be 1. Oops, just kidding. It's going to be around 7. Let me actually do this calculation. Okay. 6.99956. So if we were keeping it to 5 significant figures, that would be my pH. If I round off to 2, because I started with 2 initially, I get a pH of 7.0. Okay, so in this case, it's kind of an interesting problem. I have a strong acid, right? But does my strong acid contribute significantly to the hydrogen ion concentration? It actually doesn't, which is weird because it's a strong acid. You would think that it would, but it's such a low concentration. I mean, look at this. For every liter, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 moles of HCl or H+. So it's just not enough hydrochloric acid to actually influence the pH. It's not enough, right? Even though it is a strong acid, it's going to dissociate completely. The amount that's there is so minuscule. It's even smaller than what hydrogen self-ionizes into. And so it's just not going to affect the pH. So, like I said, you need to make these considerations as you go through these problems. You need to understand the concept. This is not a case where you can take the information, plug, and get out an answer without thinking about the actual context that's there. You have to understand the context that's there. You have to be able to evaluate what's going to affect the pH and what's not. Otherwise, you're not going to be able to calculate the right pH. Okay, so let's do the same thing for a weak acid solution. We're going to set it up the same way. We're going to make the same considerations, but our problem is going to go a slightly different direction because we have a slightly different context, right? Okay, so let's take a look at what this looks like. All right, for example, we're going to have a 1 molar solution of HF, and they give us the Ka of this. Notice in the last example with HCl and HNO3, they never gave us the Ka because the Ka is so large, we don't need it in order to determine change. We can just assume the change is complete. But in a weak acid solution, we don't know what the change is, so we need the Ka in order to help us determine the change. All right, so again, we're going to consider what's present. We have HF. We know it's a weak acid solution, so it will dissociate into some H plus and some F minus, but most likely our major contributor or our major species present in solution is going to be HF. It's not going to be the ions because it's a weak acid. We also have water present, which also self-ionizes and may or may not contribute to the H plus concentration that's there. So we're going to write out the equation. Here they have the equation written out for us. Notice they have it written out in kind of the shorthand way instead of writing it out in the actual reaction. But because we get to ignore the liquid in the K equation, it doesn't matter how we write it out. They also have the K equation written for us. Okay, so now we fill in our ice chart, ICE. What we need in order to calculate pH, we need the equilibrium position of H+, which we don't have, so we need the ice chart. All right, they tell us 1.00 molar solution initially. We're assuming this is before the reaction happens, so I have none of this. And now I get to my change. So how much of my HF am I going to dissociate, or how much of the HF is going to react with water to produce ions? Well, we don't know that. So we have to use an X. And since it's a 1:1:1 ratio, if I lose one HF molecule, it falls apart into one hydrogen and one fluoride. Oops, that should be an X. Okay, so before we go any farther, I'm going to answer a question that always comes up, which, we get into what is this, our third reaction that we've been dealing with. And the question that always comes up is it always going to be 1 to 1 to 1? Because you keep saying this, you keep considering. And actually with acids, yes. With bases and salts, no. So acids are interesting because no matter how many acidic hydrogens are present, they're always going to protonate or give off a proton one at a time. So like H3PO4 has 3 acidic hydrogens, but they're not going to be given off all at the same time. They're going to be given off one at a time, and we'll get one conjugate. And then if H2PO4 is present, it can also give off a hydrogen. And if HPO4 is present, it can also give off a hydrogen. So notice, in order to protonate all 3 acidic hydrogens, it took me 3 reactions. This is always the case for acids. Acids protonate one at a time. Now, phosphoric acid is a polyprotic acid. It's specifically a triprotic acid, whereas like HF is not polyprotic. It has 1 acidic hydrogen. It can donate one hydrogen, and then it's done, right? The anion that's left has no hydrogens left to give. It can't act like an acid. Well, that's not true for a phosphoric acid. Once it protonates 1, it still has hydrogens left, and maybe it can act like an acid under the right circumstances and give off a second hydrogen and possibly even a third. But it's going to do this one at a time with 3 different reactions. So look at all 3 of these reactions. 1 to 1 to 1, 1 to 1 to 1, 1 to 1 to 1. So acids do this. They protonate one at a time. So acids, when acids are by themselves or when acids are with water, yes, the ratio will always be 1 to 1 to 1. Now, bases, that's not the case. Bases will give all their hydroxides at the same time. Same thing with salts. Salts will dissociate all their ions at the same time. So bases will not be 1 to 1 to 1. Salts will not be 1 to 1 to 1. And acids, when they react with bases or salts, will also not be 1 to 1 to 1. So this is like a 1 out of 5 or 6 chance that the coefficients come out 1 to 1 to 1. So it's worth pausing and making that consideration every time you determine the change. Don't just get used to it being a 1 to 1 to 1 ratio, because not all reactions do this, just acids when they're by themselves. All right, so we have our changes determined. Now we can figure out our equilibrium position. So 1 minus x, x, and x. And now we can plug these into our k. So we'll get our k, which is 7.2 times 10 to the negative 4th equals x times x over 1 minus x. Okay. Again, I want to pause and draw your attention to something before we go any farther. Notice that they give us a Ka. Since they give us a Ka, you must write a specific reaction. You must write the acid dissociation reaction. So this acid dissociation reaction, or this one, is the only one that can match this Ka. So we're going to get to some examples where you have an option as to which way you want to write the reaction. Well, if they give you a K to use, your reaction must match that K. Okay, now moving forward. So now we want to solve for X so that we can determine our equilibrium positions. Now notice, if I multiply this out, I am going to get a quadratic formula situation. So I want to consider, can I make that consideration that we talked about, where x is so small that compared to an integer, it won't make a significant difference. So let's check out our k. Is our k small? Yeah, it's pretty small. So there's a good chance we can make this consideration. So x compared, added, or subtracted to an integer is probably going to be so small that it doesn't affect the significant figures. Now, x multiplied or divided, it will affect the order, like 10 to the second or 10 to the third or 10 to the fourth. So you have to keep it. Okay, so I'm going to make that assumption and see what happens. Now what I can do is 7.2 times 10 to the negative fourth equals x squared. I can take the square of both sides, and that's what I get for x. So let's do that on our calculators. Again, if you are watching this, it is the best to actually type this into your calculator and see if you get the same answer. Half the battle on these problems is knowing your calculator well enough to get it to do what you want it to do. So don't just watch me do this. Do this yourself on your own calculator. All right, so I get x to be equal to 0.02, and I'm keeping 3 sig figs, 6, 8. All right, so that would mean my HF is 1 minus 0.0268. My X for my H plus is 0.0268, and F minus is 0.0268. Now, I don't actually need to calculate equilibrium positions. That's not what I'm trying to find. I'm trying to find pH, right? So the only one I actually need is this one. Now, before we plug that into the pH equation, let's check the validity of our approximation, right? If I take 1 and subtract off what I just found, 1 minus 0.0268, and I divide it by 1, is that 5% or less? Yeah, that's 5% or less. So I can make this approximation. So now I want to find pH. It's going to be negative log of my H plus concentration, which is 0.0268. So I get a pH of 1.57. All right. Okay, we just did the same thing for a weak acid solution. So again, weak acid solutions are just a little bit more complicated because of the change. We don't know the change automatically. We have to use our K equation to figure out the change, and then we can proceed forward. So again, same calculation, different context is going to change your procedure just a little bit. So one of the takeaways from this slide is how to do it. How do we get to our equilibrium positions when we're dealing with a weak acid solution that's going to go to equilibrium instead of going to completion? The other thing that you should probably do before we move on is consider the context. Notice the context and kind of learn what's reasonable and what's not. So we had a weak acid solution. Our Ka was small, but not extraordinarily small, right? On the order of 10 to the negative fourth. We had a 1 molar solution, so our concentration is low, but not like extraordinarily low, right? We've used concentrations of hydrochloric acid in lab that were like 12 or 6 molar or 3 molar or 1 molar. So 1 is low, not super low. And then look at the pH that we got. The pH is still pretty low, 1.57, right? So if you handed someone a glass of water and was like, drink this, it has a pH of 1.57, right? You would be like, hold up, what's in here? So don't drink solutions of hydrofluoric acid, first of all. But if this was like acetic acid or citric acid, an acid that was actually edible, the pH would be low, but the acid is not super strong. It's not super concentrated. It would probably be a safe solution to drink as long as you're dealing with an edible acid, right? Not HF. HF is not an edible acid. Okay, so that's kind of the other takeaway. Let's pause, observe these contexts, and learn what is reasonable, what is normal, right? What should we anticipate as chemists as we move forward in these calculations? We can kind of get to the end and look at our acid and think, or look at our answer and think, is this a reasonable answer? So we want to be able to do that as we move on. Okay, here's another example. We can deal with this together in class. A couple more examples. And then we get to same problem, different angle. So this angle is the angle of percent dissociation. So let's take a look at this real fast. Okay, so when we talk about percent dissociation, remember any percent is always going to be a part out of a whole, right? So that's what we're talking about too. What part dissociates out of the whole amount that was initially present? That's what percent dissociation would be. And it's an interesting question for weak acids because they don't all dissociate. It would not be a very interesting question for strong acids because they do. 100%. There's your answer, right? Whereas weak acids are different. And relaying the percent dissociation can tell us something about the weak acid. Also, certain things fluctuate based on the percent dissociation. So that's what I want to show you here. What percent of acetic acid is going to dissociate? That's the question we're going to look at. So look at our example down here. We have acetic acid, we have a Ka for acetic acid, and then we have two examples here. One example where the molarity of acetic acid is 1, and another example where the molarity of acetic acid is 0.1. So we have a difference in concentration. We're going to look at the percent dissociation. And before we do this, I want you to predict. Do you think acetic acid dissociates the same amount always? Or will our independent variable here, concentration, will concentration affect how much acetic acid dissociates? Conceptually, what do you think? Mathematically, what do you think? Let's find out. Okay, so acetic acid, So acetic acid is HC2H3O2. It's kind of a long acid. And the ion, acetate, is kind of a long ion. So instead of writing all of this out, I'm going to write it as HA. Hydrogen ion times my anion, right? My anion is going to be C2H3O2 minus. So I'm going to write HA just because it's short. It's going to be faster. Now, again, we can do just a dissociation or we can do a reaction with water. H plus, A minus. I get to ignore water because it's a liquid. I'm going to set this up twice. HA plus H2O, H plus, O, A minus. I guess it's not actually H plus, it's H3O plus. But I'm going to set it up this way. Okay, so initial, change, equilibrium. Initial is going to be 1, 0, 0 in A. In B, it's going to be 0.1, 0, 0. Okay, this would be a good time to pause the video, see if you can beat me to the end. Minus x plus x plus x, 1 minus x, x, x. So minus x, 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 0.1 minus x, x, x. Now we plug them into our KAs. X squared over 1 minus x is about equal to x squared over 1. Notice I'm making the approximation that x is going to be so small, it won't actually take away any significant figures when added or subtracted to an integer. Same thing over here, Ka equals x squared over 0.1 minus x, which is approximately equal to x squared over 0.1. Now, notice, compared to the last one we did, which was HF, right? Our Ka is even smaller. Our concentration is the same. So if it was a valid approximation for our last example, it's going to be a valid approximation for this example. All right, so now we take our calculator and we plug in this information. So here, my x is equal to 0.00424. If I divide that by my initial amount and multiply by 100, I get a 0.42% dissociation. Let's see what it is for the other one. All right, this one, I get x to be equal to 0.00134, which when divided by my initial concentration of 0.1 and multiplied by 100, I get a 1.3% dissociation. Interesting. Does acetic acid dissociate the same no matter what the initial concentration is? No. The answer is no. Let me write that one a little bit more clearly. Acetic acid has dissociated more in a weak acid solution. The more dilute the solution is, the greater the dissociation. Can we explain this? What would be a good principle that we have talked about in the past that would explain this phenomenon? Let me put it another way. What's the principle we've talked about in the past that talks about when you add more of a reactant, the equation gets pushed towards products? Notice we diluted the acetic acid. A is more concentrated, B is more dilute. When you dilute something, you're adding water. We have added water. We have added a reactant. What happened to our reaction? It got pushed towards products. More ions got made. What principle is that? That's Le Chatelier's principle, right? The system is going to shift away from the stressor. Well, the stressor is water. We added extra water to this system, and the system shifted away from the water and formed products. It formed more ions. So this is always true. The concentration will affect the percent dissociation. This is always true. Okay, so that's a pretty good place to stop. When we come back together, we're going to look at a couple examples. And then we're going to kind of go back to the beginning, repeat the process in terms of bases. So let me know what questions you have. I will see you in class.